time, in 5 years back, it was not. Now it is well connected.
Within India or also
within India. Within India, it's really well connected now. In all the major cities, we have the all connection, and small cities also. It's well connected now.
I see.
In fact, Patna to Delhi, you have 20 flights every day, so it is well connected.
That's a lot. That's really a lot. What shall we do? I see that the time is come.
Wait
a little bit longer.
We just wait 2 minutes because participants are coming. Because we set them 10, so they will try to come at 10. So that takes the time lag 2 minutes to take.
No problem. Let's give a bit of slackness.
Mm-hmm. So you are in Nagoya or Italy?
No. I'm in Nagoya. I couldn't go back, even if I had to, even if I wanted to. Well, until last August. So the first big wave. So, and Italy was one of the countries that was hit first in Europe. Yeah, so people were completely, got these things completely unexpectedly, and and Italy so got the first wave very badly, and it was like March 2020. Mm-hmm. At the time, Japan closed the border when they understood that the situation was bad. Mm. And at the time, they closed the border in such a way that even if people with a visa, like I have a permanent residency in Japan, if I happened to be abroad by then, I couldn't be able to go back to Japan. So there were people that got stuck outside Japan, even with a family in Japan, with a business in Japan for months. Ooh. Then they made the things easier from August. So from August 2020. So if you had to leave, you could apply for a special re-entry permit, but they would make things so complicated with, you had to give a reason for that. So you had to give it like a family member is sick or a family member needs my help or something. So kind of stressful, right? If you don't have a reason, you don't want to make up such a reason from that. Then they require quarantine, they require the test, so only recently they're making things a little bit more streamlined for people that have that are vaccinated, but still it's quite
hard. The vaccination is not that good pace.
The idea is that vaccinations are very slow.
Yeah, there is
they just started with elderly people, but the pace is extremely slow. Extremely.
But why this is so slow? Because Japan is one of the countries why? There's some other reason. I
learned that there is a kind of aversion against vaccinations since the 80s. There were some cases and people got scared. People are not so, the public opinion is not so positive with vaccinations.
Okay, that's
so the government is extremely careful before suggesting a new vaccination campaign. They're extremely careful. If anything would happen, they would take responsibility and they would lose the next election probably. So no one would really want to take the responsibility, and things are slow. The bureaucratic machine in Japan is extremely slow. There's a big inertia.
Yeah. So how did they then arrange this Olympic? That's an interesting thing, because but that's still.
They will hold the Olympics with empty stadiums, with no people around. Probably also this is the reason why they want to keep the country frozen. Because if they get too fast with vaccinations, then they should change the policies for the Olympics. So now everything is done. Everything
they have invested $1 billion.
Everything is scheduled, and so they have to keep the country as it is now until the end of the Olympics and Paralympics games. Probably there is also this reason going on. They cannot cancel, because if not, they should pay the Olympic Committee billions of dollars in compensations. And they are not ready to pay billions of dollars for that. So I think that, there are not so many things that can be, not many alternatives.
Okay, Francesco, it's 10:05. So just I wanted to tell you one thing, maybe Professor Panikri has already told, that is you have the questions in the chat box. Either you can read them or I can read it for you. There are there are some questions in the YouTube channel. So if there's YouTube channel, so that I will read it for you. I don't need to read.
Okay, very good.
So if you want, then you can read it from here.
Yes, I would. Ideally, I would like to take questions as they come.
Okay,
like I can be interrupted.
Directly.
The point is that if there are too many questions, that the presentations get stuck because of the too many questions.
That I will take care. That I will take care. But some questions you may allow in the I mean during the talk, right?
Yes, actually can be good. You know, I will be telling things that are mostly conceptual, and so they might stimulate many questions. And also for me, these are things that I'm keep thinking day by day. So you know, questions are very natural. When you go into the second law of thermodynamics, then there are questions that.
Yeah, there are mostly students, undergraduate and some PhD and postdocs. So there, we expect there will be many questions. So Professor Panikkar, should we start?
I'm ready. Anytime you like.
Yeah, I think, look, start. We have around 100 now, 99. 100.
Okay. So let me start by introducing Professor Buscemi. And good morning to everyone and welcome to this session. In fact, I am so happy to get this opportunity to introduce him. And as I was telling that I first met him in Nagoya University in 2014. And he had also come to our Patna conference. Every time I met him, it was actually a very pleasant meet. And he's a very humorous and fun-loving person, as we know.
So kind. Thank you very much.
Yeah, it is our great pleasure to have him with us today. And we thank him very much for accepting our invitation. Professor Buscemi is currently a professor at Nagoya University in Japan, and he obtained his PhD from Pavia University in 2006 with Professor Dariano. And he was a postdoctoral fellow at University of Tokyo from 2006 to 2008. And then he moved to Cambridge University in 2008 as a postdoc. And he stayed there until at the end of 2009. And then he moved back to Japan in 2009 at Nagoya University as a tenure track professor. And then he became professor there in 2019. Professor Buscemi has many fundamental and important contributions in the field of quantum information theory, quantum foundations, quantum thermodynamics. In fact, his work, these all entangled states are non-local, and that gave him in 2012. Yeah, it gave him a wide recognition in the field. In fact, it introduced a new topic, that is measurement device independent certification. He has also worked in many different topics and made many important contributions in quantum foundations, quantum measurement, uncertainty principle, quantum thermodynamics, hypersignaling theories. And he is a recipient of many grants and the award, including the Birkhoff Tournament Prize in 2018, and that is awarded by International Quantum Structure Association. And he served as an editor of many international journals. And currently in the editorial board of Physical Review X Quantum. And he's a highly rated journal. And I must also say that he's an excellent teacher. And in fact, Nagoya University, I mean, this weekly seminar, he used to give us a lecture every week. And if the lecture is not for the 1 hour, it was for the 3 and 4 hours. So it was excellent, Francesco. And
thank you.
Today, it is our great opportunity to listen to him. And he will be talking about this prediction, retrodiction, and the second law of thermodynamics. And with this, I would like to invite Francesco to give his lecture.
Thank you very much, Alok, for this kind, very kind introduction. Now you're putting, using all these nice words, you're putting on me a big pressure that I have to give
you are an excellent teacher.
Worth your introduction. Right? Okay, so let me share the slides. All right. So very good. And you can also see the pointer, yes?
Sure.
The pointer. Okay.
Yeah, I can see the pointer. Yeah.
So today my talk will be mostly conceptual, and I think it's a good thing for a school, right? Rather than teaching, calculations or things, I would like to tell you something that I've been thinking very much lately, and it is about thermodynamics, especially because I am interested in how can we understand thermodynamics in the quantum regime. But this led me to question also some aspects of classical thermodynamics and statistical thermodynamics, in particular, the role of the second law, how the second law is constructed, what does the second law tell us, and so on. So today I would like to bring you with me in this deep dark wood, like in the Gruffalo's bed story, you know, the mouse took a stroll in the deep dark wood. And today I would like to bring you along with me in this deep dark wood, but full of very interesting ideas. And I hope that I will be able to pass you some messages that I believe are new, or at least have not been highlighted so much before. So this is work that has been done mostly in collaboration with Valerio Scarani from the National University of Singapore. And we put on the archive 2 papers by now on this line, about this line of research. One paper that has been published in Physical Review E, and another paper which takes a more radical stance on these ideas, which has been instead uploaded only on the archive for the time being. Okay, so let's start with a kind of parable, a kind of introductory story. So you might have heard, especially if you are from physics background, you might have heard of this surprising result that was obtained in Fermilab that displayed an anomaly in the physics of the muon, an anomaly that would contradict the standard model, which is the best model that we have to describe fundamental interactions in physics. So essentially, this experiment is falsifying the standard model and is pointing towards the existence of new physics. So the result is extremely satisfying, but no one has questions about the validity of this experiment. And actually, everyone is looking up to this result as a very exciting thing, because it's pointing towards new physics. But what about, for example, if I show you something very similar as far as the news is concerned, as far as the format is concerned? Well, we have to change the newspaper. So we have to go to the Daily Mail, to the tabloid, the infamous British tabloid, the Daily Mail. But in 2016, so just 5 years ago, they published a story whose headlines look similar to the headline before: New Physics, a step towards limitless energy, loophole found in a fundamental law of physics. As before, there is a loophole found in the standard model. But here, what is the law of physics which is violated? Is the second law of thermodynamics. So then when we violate, or where there are claims that people can violate the second law of thermodynamics, usually these are met with a raised eyebrow, right? Like, no way this can carry through. But I would like to think together with you why we assign such a special role to the second law of thermodynamics against other laws of physics. Why we believe that the standard model can be falsified, or general relativity can be falsified. You know, we have big bangs, we have dark energy, dark matter, things that we cannot explain, but we tend to believe that these observations are real, right? True, faithful. But if someone comes to you with a perpetual motion machine, then you start thinking that this person has to be a crackpot, right? So the perpetuum mobile, a Latin word, means perpetual motion machine. There have been many proposals of these things, right? And no one works. Even Leonardo da Vinci actually spent some time, as a pastime, I would say, in designing some perpetual motion machines. Here there are some sketch of something. You can find some videos on YouTube of people that build up this proposal of a perpetual motor machine by Leonardo da Vinci, but he knew that perpetual motor machine would not work, even though, of course, he was not aware of the laws of thermodynamics, but he already had this kind of intuition. So it's very surprising how someone that came 400 years before the formalization of the laws of thermodynamics could already have this intuition that perpetual motor machines, and therefore like second law of thermodynamics, are things that you cannot have. He has this sentence: "Oh ye seekers after perpetual motion, how many vain chimeras have you pursued already? Go and take your place with the alchemists that were already another branch of science in which he didn't believe so much. So he was a very modern man. And indeed, still now, we have the kind of this deep feeling that the second law of thermodynamics is special among the laws of physics. And Arthur Eddington actually wrote this explicitly in his book. The law that entropy always increases holds, I think, the supreme position among the laws of nature. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it to collapse in deepest humiliation. But also Albert Einstein, when speaking about thermodynamics and the second law, he would say, this is the only physical theory of universal content concerning which I am convinced that within the framework of the applicability of its basic concepts, it will never be overthrown. But why? So I would like to try to understand what is going on with the second law. Okay. Some people even put the second law on pair with Shakespeare's work. Charles Snow, in his essay "The Two Cultures," he wrote this that people know about Shakespeare's, but people don't know about the second law. They don't feel bad if they don't know about the second law. But he would say that asking someone, do you know the second law of thermodynamics, would be equivalent to asking, have you read a work of Shakespeare's, right? So what is the to be or not to be of thermodynamics that everyone should know, all right? And I would say that this is the second law of thermodynamics, even more than the first law that expresses, the conservation of energy. The example, the paramount example of a physical law that everyone knows, but typically everyone uses in the wrong way, is the second law, second axiom of thermodynamics. And by the way, I would like to stress that this is an axiom, and this axiom is about basically the non-existence of perpetual motion machines, right? So the first myth that I would like to dispel is that perpetual motion machines do not exist. You hear a lot that perpetual motion machines do not exist because they violate the laws of thermodynamics. But I would like to stress, to point out that this way of explaining things would just bring you in a logical loophole, in a circular argument, because the laws of thermodynamics axiomatize the inexistence of perpetual motion machines, right? The second law of thermodynamics are axioms. Essentially, they tell you that you cannot win, that there are no free lunches when dealing with energy, right? So we have to go deeper, right? Okay, so I'm speaking too much, okay? So let's see the formula of the second law of thermodynamics. Everyone knows, oh, I see a raised hand already. Okay, please ask the question.
So this question may be a bit too early, but you know that the second law of thermodynamics is inherently related to the concept of entropy, that entropy of the closed system should always increase, or the entropy of the universe should always increase. But at the same time, entropy is related to information. So entropy increasing is basically information getting deleted. Whereas Leonard Susskind, as he mentioned in his negative first law of thermodynamics, he says that information can never be created nor be destroyed. So is it not violating the second law of thermodynamics?
Is this violating the information thing?
Yes, I'm asking about, because information is inherently linked to the second law of thermodynamics. That is, the total amount of information must start to get deleted because entropy must increase. So, and
yes, but my question is why entropy must increase? I would like to go deeper. I'm not happy just to accept the second law of thermodynamics as it is. So the story that I'm going to tell you today is how we can understand why entropy increases. Of course, if you accept the second law of thermodynamics as an axiom, it's fine, but you have to understand that you're accepting an axiom. So I would like to point out where the second law of thermodynamics is special among the laws of physics. This is the story that I want to tell you today. And indeed, here I put these things about entropy just because everyone thinks that the second law is about entropy, right? And entropy increase, and people can be more or less precise. Like, you know, the layman would say, oh, entropy increases, but then someone would say, what about your fridge then? Your refrigerator causes a local decrease of entropy. So then you would have to put like the total entropy, like the entropy of the system, and the surrounding environment is going to increase. But then when you start thinking statistically or stochastically, when you start introducing notions of statistical mechanics and stochastical thermodynamics, then you understand that entropy is a random variable that fluctuates. And so you have to think about its average fluctuations. And the average fluctuation of delta, the entropy, the average entropy increase of the total system cannot be negative, right? It must increase in average. But still, you know, I can formulate the second law mathematically as precisely as I want, but still it does not explain me, or I'm not happy with that because it doesn't tell me why the second law of thermodynamics feels so special among physical laws, so special that even Leonardo da Vinci, for 100 years before the formulation of these axioms of modern thermodynamics, classical thermodynamics, would already have a kind of like original notion, innate notion of the validity of something like the second law of thermodynamics. So this is the question, right? It's not, you know, the interpretation of entropy. The question is why the second law is telling us something so natural that we are absolutely sure that if someone is claiming to violate that, that is going to cause some contradiction. So is entropy really the key to understand the second law? So many explanations of the second law actually amount to explanations of entropy. If you search on YouTube, now that we are stuck at home because of pandemics, we are watching a lot of YouTube videos. And if you're interested in physics and foundations of physics like me, you might have searched for many of these things on YouTube. And there are many beautiful channels there, and many of them, of course, they deal with the second law of thermodynamics and the arrow of time, these extremely fascinating concepts. But typically, when it comes to explaining the second law of thermodynamics, they just explain the notion of entropy, using, for example, counting arguments, right? Or decks of cards. But it is always about entropy. The problem is that no one understands entropy very well. This is an apocryphal, this is something that von Neumann seems to have said at some point to Claude Shannon. There are people that do not believe that this is a true fact. Actually, also Shannon would not be able to remember exactly when this happened. So I would say that it's just an apocryphal attribution to von Neumann. But in any case, even if one would understand entropy very well, that would only be the half of the story. Because we would understand entropy, we would understand that these things do not decrease in average, but still we would not understand why the second law is so special. So let's get rid of entropy for a while, and let's see that actually the second law need not the entropy to be formulated, right? The typical idea here is that you start with a system in thermal equilibrium, like an ideal gas with no phase transition, like an ideal gas of ideal particles that undergo ideal motions with ideally elastic interactions. So you start with a piston in this position and a gas in thermal equilibrium, then you isolate the piston from the surrounding thermal bath, and you plunge the piston in, driving the system out of equilibrium. If you imagine that your system is made up by a little number of particles, this is going to become a kind of statistical experiment. So every time you plunge the piston, you will have a slightly different reading of the work that you have done to plunge the piston into the piston inside, inwards. And so you can have, you know, that the average work you will find out that Clausius inequality that was formulated in 1865 tells you that the average amount of work that you do on the system is lower bounded by the difference in free energy, which is the energy that can be stored when the system is in equilibrium. So it came as a surprise that after 130 years, more than 130 years, after so many people have thought about this point, actually just by moving these terms around, one could turn an inequality into an equality. And this is the celebrated work by Jasinski that was published in 1997, where he shows that actually the average of the exponential of work is equal to the exponential of the difference in free energy. And then the second law, Clausius inequality, comes from Jasinski inequality just by the concavity property of the exponential function, or well, convexity property of the exponential function. There is minus sign. So the idea is that if we want to dig deeper into the second law of thermodynamics, we have to start thinking in stochastic terms, in statistic terms. So then work is not anymore something that is well defined by the process, but it is a random variable itself that fluctuates. And so you have a distribution of possible values of the work. And Jasinski tells you that the average of the negative of the work with this work distribution is equal to the exponential of the free energy. And Clausius just tells you that the average of work is greater or equal than the difference in free energy. But let's dig deeper. And we are not happy to stop here. This will not give us still a great understanding of what's behind the second law. So in modern statistical mechanics, there is another result that had a comparable impact to what Jasinski equality had, and this is Crooks fluctuation theorem. So in order to formulate Crooks fluctuation theorem, now we have to consider not only the forward process of plunging the piston inwards, but also a reverse process of pulling the piston outwards. So given a forward process, we construct a reverse process in this way. And now Crooks fluctuation theorem that was published just 2 years after Jasinski equality tells you that the ratio of these two probabilities, so the probability that you are going to do a work W on the system in the forward process, so the process of pushing the piston inwards, divided by the probability that you do a work minus W, or equivalently, the probability that you obtain from the system a work plus W in the reverse process of pulling the piston out, the ratio of these two probability distributions, probability densities, is given by this exponential. This is something extremely powerful, extremely insightful, and thinking that beta for room temperature is a number of astronomical size, is like 10 to the 23, then we understand why these fluctuations, like these, the forward process and the reverse process, are extremely unbalanced for the situations that we experience every day, right? And in fact, this unbalance in the work distribution for a forward process versus the work distribution for the reverse process is what implies Jasinski equality, which is in turns what implies Clausius inequality, which is the second law, right? Once we got rid of the entropy, which is just a way to formalize Clausius law for open systems. Huh? So I would say, and people agree, that in order to understand what's behind the second law, to understand when the second law holds and when it does not hold, because people are proving the validity of the second law in particular systems, right? It is something that you have to prove. We have to understand what's behind Crooks fluctuation theorem. And the usual explanation is that Crooks theorem, and hence Jasinski's relation, and hence the second law, all rely on two assumptions that are satisfied at equilibrium, thermal equilibrium. The first assumption is thermal distribution. That tells you that at equilibrium, the probability of being in macro state psi is proportional to the negative exponential of the energy that correspond to microstate psi. And we know that this can also be understood from a epistemic viewpoint by using Jane's maximum entropy principle. The thermal distribution would be the minimum committing assignment to the distribution of microstates that you could give, given the data in the form of average energy. But also there is another assumption that is crucial in the proof of Crooks fluctuation theorem. It is the assumption of microscopic reversibility that is extremely closely related, though somehow slightly different from the condition of detailed balance at equilibrium. That tells you that molecular processes and their reverses occur at the same rate at equilibrium. But again, I cannot understand why the second law feels so special. Is that because of this kind of special microscopic balancing mechanism that happens at equilibrium, so that forward process and reverse process at equilibrium happens at the same rate? So is it really something that we have to understand some property of the microscopic interactions? So here I would like to take instead, and this is the core of my presentation today, I would like to take a completely epistemic stance on this problem. So I would like to follow James, who wrote in 1984 in his paper Predictive Statistical Mechanics, he wrote the following thing that it is extremely inspiring for me. He writes, to understand and like thermal, we need to see it not as an example of the n-body equations of motion, but as an example of the logic of scientific inference, where scientific inference for James means probability theory. James is one of the main advocates for the Bayesian approach in probability theory. And the first idea that we had with Valerio was to try to see the second law as a balance, not between a forward process and a reverse process happening physically at the microscopic level, but as a balance between a forward and a reverse inference. So as a balance between prediction and Bayesian retrodiction. So now I would like to introduce to you what we mean by Bayesian retrodiction. So we have to start from Bayes' Laplace rule, which I'm sure many of you know is written as follows. So Bayes' Laplace rule essentially tells you how to update your prior probability that essentially models your prior belief about the hypothesis, the possible hypothesis H, given some data. So you have to imagine that you are given some piece of hard evidence, D, this data D. So Bayes' Laplace rule tells you how you should update your belief about the causes that were behind the data, the hypothesis that gave you the data. So here you have the prior and here you have the likelihood or the model. This is something that is fixed by your physical model, right? And the inverse probability is proportional to this, right? So a lot has been said about Bayes' Laplace rule. I mean, the problem of understanding the assignment of the prior distribution has been beaten to death. And people have been fighting very harshly in the past century between the two camps of Bayesian statistics and orthodox statistics, also called the frequentist approach to statistical analysis. But I would like now just to use Bayes' Laplace rule as a tool. Like nowadays, we use Bayesian statistics as a tool, so we don't need to subscribe to any ideology if using Bayes' Laplace rule. We are in a postmodern world, and so this talk will be using postmodern Bayesianisms. We will be using Bayes' Laplace rule as a tool and see where it leads us. As a tool, the inverse probability is at the core of Bayesian statistics, and it is used to solve problems like estimations. For example, answering questions like how many red balls are in an urn of which you don't know anything about its content. Basel plus rule is the tool to use in decision problems. For example, is this company's stock a good investment? Should I buy some, and how much of my portfolio should I allocate to these companies' stocks, right? Something like that. But also, and more importantly, Basel plus rule can be used for inference and learning. And you have, in this case, you have two main branches here. You have predictive inference, that it is an inference that is aimed at predicting what will happen in the future, for example, weather forecasts. But also retrodictive inference. Retrodictive inference is nothing exotic, is no black magic. It is something that is, actually there are entire branches of physics that only rely on retrodictive arguments. For example, astrophysics, astronomy, cosmology. We don't have any ways to prepare two cosmological bodies and make them interact, two black holes, and see how they interact to make experiments and predict what will happen, right? We can only just look at the sky passively for data to come to us and retrodict what was behind those data, what was the cosmological event that caused our observations. And if you subscribe to the interpretation in terms of degree of belief, you can say that Bayesian statistics measures the degree of belief that a rational agent should have in one hypothesis amongst other mutually exclusive ones. However, Basel plus rule does not tell us how to update the prior in the face of uncertain data. What do I mean by that? So suppose that I have a situation in which my data would be the license plate number of this car. So as you see, this picture is very noisy. So I cannot really say that I'm reading any particular number here, but just I can say that there is some probability there. Maybe the first letter is an A with a high probability, but I'm not completely sure. So there are situations in which the data are not given with certainty, but are given only in an uncertain way. And Basel plus rule does not tell us anything about how to deal with those data, right? Because for Basel plus rule, you should put in the place of that placeholder D, you should put some definite value for D. If not, it doesn't work. All right, so the question is, how should we update the prior given uncertain evidence? And this is the core of Bayesian retrodiction. So for that, we need something new. We need an extended Bayes rule that tells us how to deal with uncertain data, given in the form of the probability distribution QD. And this rule is given by Jeffreys conditioning, which was proposed ad hoc. It was introduced ad hoc as an ad hoc extension of Bayes' rule in 1965. That tells you essentially that you can take, actually you should take, the inverse probability that Bayes' theorem tells you and use it not as a probability assignment, but as a noisy channel that propagates your uncertain data back onto the hypothesis. So you see that this is exactly how a noisy channel in information theory works. You have a conditional probability of H given D, which is the inverse probability of Bayes' rule. But now this is used not as a probability itself, not as your posterior itself, but as the channel that propagates your belief in the data, QD, back onto the hypothesis. Actually, Jeffreys' rule can be proved from Basel plus rule and Peirce method of virtual inverse, but that's a different story. So let's say that now we have a way that is able to back propagate uncertain evidence from the data to the hypothesis. And we will use this to construct our reverse process. So we want to imagine a situation where physics only set the stage So the physical setup will give you a stochastic transition rule that tells you how the macrostate X will, the likelihood that macrostate X will end up in macrostate Y. This is given by your physical model. And this will come with a steady state, also called invariant distribution, that we denote by S. Okay, so this is what physics tells you. And now I would like to take a completely epistemic viewpoint here, where processes are actually inferences. The forward process and inference being done forward in time, so a prediction, and the reverse process as an inference instead done backwards in time, that is to say, a retrodiction. So the reverse process will be constructed at absolutely not. It will be constructed at a steady state, at the invariant distribution. So here, by this relation, we define what this reverse stochastic transition matrix is, this phi hat. We are using the product rule of probability. And this relation defines phi hat. So why we construct the reverse from the steady state? Because the steady state is the situation where prediction and retrodiction coincide. So we want to construct the inverse process at the situation where the predictor and the retrodictum would agree. And now we give two priors, which are different from, in general, are not the steady state. Okay, this is an important one. The two priors are arbitrary, okay? And one is given to the predictor, is the predictor's prior, Px, and the other is the retrodictor's prior, Qy. And using the forward process, the reverse process, phi hat, the predictor's prior, and the retrodictor's prior, we can construct two processes. The forward process, which is this, so it would be the process predicted or inferred by the predictor. And the reverse process would be the process instead inferred by the retrodictor. So a picture is the following. So here we have two boxes. We have the forward process and we have the reverse process. So if the predictor starts from the steady state of the process, these will completely agree with the retrodictor starting from the same steady state as. But if predictor and retrodictor start from something that is not the steady state, then an asymmetry is there. And this asymmetry is there because Bayes' Laplace law, because of the way Bayes' Laplace rule looks like, because we can basically prepare conditions and propagate them in the future, where typically you cannot prepare final condition and back propagate them to the present. So there is the asymmetry here is something that is intrinsic to logical inference. So this asymmetry that we can call irreversibility, but has nothing to do with the reversibility of the microphysics. This is something that we don't care about, okay? This is irreversibility of the inference. So I would rather like to call it irretrodictability, to use a term that was used by Watanabe in 1955 in a paper in which he considered, for the first time, to my knowledge, the problem of the difference between prediction and retrodiction. And then the second idea is to measure statistical divergence, to measure fluctuation relations as measures of statistical divergence between predictor and retrodictor. This is something that is not new. This is done, this has been noticed already. But the point is that taking this epistemic stance of, leaving from the typical, thermal interpretations of work and heat and energy and so on, we are also encouraged to depart from the usual definition of relative entropy, that it is the one that is usually used, right, where you use to describe the difference, the statistical difference, the relative entropy. Instead, one is encouraged also to use different relative entropies, for example, F-divergences, that still, again, use this ratio between the two probabilities to measure the statistical divergence. So now you see that this relative entropy is actually the average of this thing, which can itself be thought of as a random variable associated with your process. This ratio is itself a random variable, and its average is the statistical divergence between forward and reverse process, or between prediction and retrodiction. Then you can formally, even though this number is a discrete random variable, you can formally introduce a continuous probability density function by using the, this delta function here. And you can work out things for F-divergences, and you can actually work out F-fluctuation theorem. So fluctuation theorem does not hold only for relative entropy, but it holds for more general F-divergences. So you see that looking at things already from the outside comes with its merit, right? Because you are encouraged to see what really is at stake there. In particular, if you take this function to be the negative logarithm, then the f to the -1 is the negative exponential, and you fall back onto typical Crooks fluctuation theorem and Jarzynski equality. But this is, like a kind of side result. This is not really the main message that I want to tell you. The main message is that rather than working with a physical thing that is going on microscopically, a forward process and a reverse process, things can be understood instead only at the level of logical inference as prediction and retrodiction. And indeed, if you apply this way of thinking to known results, you recover them all. You can recover Jarzynski relation, you can recover Crooks fluctuation relations, you can recover also, for those of you who are aware of it, Tasaki to measurement formalism of quantum thermodynamics and so on. So for example, just to show you how a retrodictive argument can recover fluctuation theorems for closed-driven evolution. So you have a driving protocol that drives the Hamiltonian of your system from h0 to h tau. And let's say that h0 has these energy levels, and h tau has this energy level instead, eta y. Now, because this is a closed system, even though it is driven, it is still Hamiltonian evolution. And so the evolution is one-to-one, right? So this stochastic transition matrix is actually a function. It is a delta of y and the evolved version of x. So it's a one-to-one, it's a function, actually. So for example, you can take, in this case, you can take as a invariant distribution, the uniform distribution. Like if you imagine it in the quantum regime, you can imagine that the evolution here is unitary. And so as stated, it is left invariant by unitary is the maximally mixed state. So you start from that invariant distribution, and so you come to the conclusion that the retrodicted process phi hat, it is given by this formula, right? So phi hat of x given y, it is equal as a number to the the forward process y, phi of y given x. And now we give to the predictor and to the retrodictor as their priors, we give the thermal distributions, which are not the steady state with respect to which I constructed phi hat. But if I do this, which is what is done typically, you remember in my slide about Crooks fluctuation theorem, the system was driven, was closed, and the initial state for the forward process and the initial state for the reverse process were both taken to be the equilibrium, the states at thermal equilibrium. So here we are doing the same, and we're constructing the forward process, the prediction, with the forward process and the thermal equilibrium, and the same we are doing with the reverse, the retrodiction with the reverse process. This number also goes away, and you are left with the logarithm of px divided by qy, which due to the thermal assumption gives you a difference of energies plus a difference of free energies, phi dash. And F dash, F and F dash. And because here the system is closed in the sense that there is no exchange of heat, all changes in internal energy can be understood as change in work, as work provided to the system. And so we understand that this fluctuating variable is exactly the work variable. And we get Crooks fluctuation theorem. Even more interestingly, you can describe non-equilibrium steady states. So you imagine a process with a steady state that is not uniform, is not thermal in general, some Sx, and you do the same as before. The difference now is that these numbers will not go away, right? Because this is not the uniform distribution anymore. So you have to keep them in the balance in the definition of the fluctuating variable omega. And these numbers, what are they? Look, they coincide with the non-equilibrium potentials that are used, for example, in Hatanov-Salsa fluctuation relations, but also are introduced here, are considered in this paper 2015 by Banzano, Parondo, and Horowitz. So typically, these non-equilibrium potentials are introduced ad hoc to make fluctuation equality go through, because if you were not using this non-equilibrium potential, you will have something that is not one. You will have something that is known in the literature as efficacy, but I would understand it now as just a way to do retrodiction in the wrong way. Because if you do things in the right way, that is to say, if you do things according to Bayes-Laplace rule, these non-equilibrium potentials emerge from Bayes-Laplace rule and are understood here not as just ad hoc corrections that you have to add to the change in internal energy of the system, but are remnants of Bayesian inversion. So the question is now, but why then known relations are compatible with Bayesian inversion? Is it a necessity or just a coincidence? And here it is a very sketchy argument for the necessity of a retrodictive argument in fluctuation relations. So start from the definition of fluctuating variable, which was this thing here, right? Which describes this asymmetry between forward process and reverse process in terms of prediction and retrodiction. So if we impose that this quantity is local in the sense that it can be written as a difference of a function evaluated for the final macrostate and another function evaluated for the initial macrostate, then we are necessarily led to the conclusion. You can follow these steps one by one, and you are naturally led to the conclusion that the reverse process has a form of Bayesian inverse with respect to PF for some prior h of x. So a Bayesian inverse-like form for the reverse process is inevitable if we want a fluctuating variable to have a local form. Local in this sense has nothing to do with, entanglement or Bell locality. No, local in this exact sense. So if you want this fluctuating variable to be a difference of the functions. And finally, what about the quantum case? So I would like to conclude by showing you that also in the quantum case, if we use a correct notion of quantum retrodiction, then we can just understand quantum fluctuation relations very naturally. Instead, it is something that people are still, trying to find out what is the correct formalization of quantum fluctuation relations. So assume that the model that is giving you the stochastic transition rule is quantum. That is to say that you have some mechanism that prepares some quantum state rho x, and then some kind of evolution that is described by this map E, and then finally some measurement py that gives you, the underlying physics that describes your stochastic transition matrix, your stochastic transition rule. So let again, as before, Sx be the invariant distribution of this classical stochastic transition rule. And now we can just apply the formalism of quantum retrodiction that we do not invent, but we took from previous literature that dates back to work by Barnett in 2000, and then it's been used by Crooks. It's been proposed by Leifer and Speckens in the paper about a causally neutral formulation of quantum mechanics. But quantum retrodiction is something that resurfaced a lot in the literature of quantum information theory and quantum foundations. And the core of it is the use of this reverse process we had that coincides with something that is known as Pet's recovery map. So if we use quantum retrodiction, Bayesian inversion works seamlessly also in the quantum regime if we pay attention to use as the reverse process the corresponding Pet's recovery map done with respect to the invariant distribution, right? So some remarks about quantum retrodiction. So this Pet's recovery map, so this rule here that is taken from the literature of quantum retrodiction reduces to Bayesian plus rule when everything commutes. So it is just the Bayesian plus rule. It is nothing exotic. The difference is that to a unique Bayesian plus rule that corresponds infinite possible Pet's maps. And these Pet's maps are somehow, I mean, still the core is that of a Bayesian inversion, but you have some rotations going on. So these are called rotated Pet's maps. And the point is that retrodiction, both classically and quantum, depends on the choice of reference priority. This is something unavoidable, that it is there intrinsically because of the structure of Bayesian plus rule, which means the structure of logical inference. There is nothing we can do. Prediction and retrodiction are different. They are asymmetric. And this is the asymmetry that the second law is telling us. Exceptions to this, so exceptions to the infinite number of Pet's map and the dependence of the reference priors are unitary channels, which are called by Watanabe bilateral deterministic channels, for which there is a unique Pet's reverse. And indeed, you know, unitary channels are deterministic channels, are functions. There is no randomness going on there. And so it is very natural to imagine that their reverse does not depend on the prior that you use to reverse them. They have a well-defined reverse independently of your belief. And for unitary channels, retrodiction and linear inversion coincide only for unitary channels. Otherwise, typically channels are not invertible as linear maps. So even though they could be invertible as linear maps, their inverses are not channels themselves. What you do to invert a channel, you retrodict the input. Even in classical communication theory, if you are at the receiver end of a channel and you see a letter, you are not trying to invert the matrix, the stochastic matrix that propagates, you know, the input distribution to the output distribution. You are retrodicting. You're trying to learn the input. It's a completely different process. Unfortunately, reversal, inversion, reversion, they sound awfully similar, and I think this similarity is at the root of many confusions. Conclusion. So final messages. Let's see if I was able to, you know, convince you that the second law is special. And we mean why the second law is special, and indeed why it plays a special role among the laws of physics. So first of all, the first message is that predictive and retrodictive inference provide the logical foundations of fluctuation theorems. The second point is that the second law is special among the laws of physics because we can understand it being in fact a law about the logic of inference. So if you violate the second law, you're not violating a physical law, you're not violating Maxwell equations, so you're not breaking the standard model. You're breaking the laws of logical inference. So it means that you are reasoning in an ill-formed way, leading to the contradictions down the way. logical contradictions more than physical contradictions. Point 3, that reasoning in this way allows you to introduce a clear distinction between mechanical irreversibility that might or might not hold. We don't know. I mean, we've never observed a quantum process going on. The unitarity of quantum theory or the unitarity of Schrödinger equations is something of a postulate. No one has ever observed, what is really going on deep down there, right? So the underlying physics could be irreversible, we don't know. But the second law arises from the irretrodictability given uncertain knowledge about the microstate, right? Given that we don't know exactly what's going on deep down at the bottom, the observed irreversibility or asymmetry of thermodynamics comes more from a phenomenon of irretrodictability. So there is no paradox, like Loschmidt paradox. How can irreversible laws arise from reversible underlying mechanics? Because we're speaking about two completely different things. And also that quantum retrodiction and quantum fluctuation relations follow seamlessly using Pet's recovery map. So until now, people have been using Pet's recovery map as, something that if you plug into some equation, you get something that reminds you of the Jaginski equality, but there was no reason as to why one should use Pet's recovery map there. And the reason now is that we can understand it as because due to the fact that Pet's recovery map is what you do in quantum theory to do quantum retrodiction. And also this would explain why Pet's recovery maps is popping up as a mushroom in all fields of physics. Before it was introduced by Petz just to deal with the monotonicity of quantum relative entropy, but now it's used everywhere in black hole information paradox, in many-body systems, in quantum thermodynamics. Why? Because it is not something that is there only for information theory, but it is how we do retrodiction in quantum theory. And that is it. And I thank you for your attention. I'm sure there will be questions, so feel free to ask.
Yeah, thank you, Francesco. It's a beautiful talk. There are only one question at this moment. So we may take a look.
Okay, I see the question. If we leave a completely isolated system with zero entropy for trillions of years, is it safe to say that at the end the system must have zero entropy? Each time has some effect on entropy. So it seems that here the person asking this question is thinking of entropy as a property of the system, whereas entropy is really something that is a property of your knowledge about the system. This is something that has been debated a lot. This is statistical mechanics. But I would say that nowadays, I would tend to agree with James' approach. He was not the only one, but at least it was I would say, the person pushing these ideas more aggressively, that entropy is something that has to do with your knowledge of the system. So I would say that this question doesn't make so much sense if we imagine. So if your knowledge of the system is complete for 1 trillion years, then yes, that system has still zero entropy for you. But for another observer that knows nothing about the system, the entropy might be a lot. So the entropy is ultimately a observer-dependent concept, not a quantity of a physical property of the system. This is the way I would answer this question. Yeah. So another question, why did the universe have such low entropy in the past, and time correlates with the universal increase in entropy from the past to the future according to the laws of thermodynamics? Okay, this is a great question. to which I don't have myself an answer. Actually, so this idea of understanding the second law in terms of prediction and retrodiction would lead you to the conclusion that if there were hypothetical creatures that were living instead in a reversed time universe, right, they would still observe an increase in entropy for them. For them, the future would be the situation where you can prepare, and then they would observe the future evolving to the past. So for these kind of creatures that were able to prepare future conditions and let them evolve towards the past, they would still observe an increase in entropy for them. They would not see contradictions of the second law of thermodynamics. So it seems that from this point of view, the second law of thermodynamics has nothing to tell you about the physical arrow of time. There is no such a thing. There is only a logical arrow of time at stake in the second law of thermodynamics, if you're happy to embrace this viewpoint. However, there are things that we observe in the universe that seems instead to have a well-defined arrow of time. Typically, it's the cosmological arrow of time. There has been a big bang in the past and the universe is expanding. I don't know how to answer that question. I would like to be able to understand sometimes in the future that universe expansion is also a necessary consequence of our way to do inference. That there is nothing physical there going on. There is no physical process expanding space-time, but it is something that has to do with the asymmetry of the laws of inference. But, you know, I'm very far from even trying to grasp these kind of things. But this is what I would like to think, like there is no definite arrow of time. Everything that you see about arrow of time is about our logical arrow of time. The way we learn from past to future, we never learn backwards. Oh, RCP violation somehow a product of the second law of thermodynamics. Also, this is another interesting point, right? Because people are using, I mean, I saw papers, I myself am no expert in this. I just read a lot in the past couple of years, right? But I would not call myself an expert in this, in the foundations of statistical mechanics, which is a mess, right? But I've seen papers discussing the possibility of formulating fluctuation theorems for systems that violate time inversion symmetry. So here the point would be that, like, that's exactly the point. Like the second law, like this, what we call the reverse process. If we are in a situation like every day, like the inverse process, this retrodiction is really something that we can think of, like looking at things, how would they go in the past? But this is not the movie showed in reverse order, right? This is something completely different. So for example, if you have a system that does not satisfy T symmetry, but satisfies more complex symmetries, then you should do retrodiction according to those more complex symmetries. If you do retrodiction only only constructing retrodiction using the time, then you would be doing a wrong retrodiction, right? So yeah, like again, I would like really to divorce what is going on at the physical level from what is going on instead in our process of learning about the actual process. And I would like to say that the second law has more to do with our learning about the process, which is a noisy learning. It is a learning that necessarily does not have full knowledge of the system that is evolving, rather than being a law that has to do with the actual propensity, some kind of physical propensity of the physical system to evolve towards equilibrium, rather than not. So this is my way of understanding the second law now. at this point in time that I'm talking to you. Then maybe, you know, tomorrow I will learn something different and I will become more, I know, closer to the orthodox understanding of the second law as the laws of physics. But by now, I like a lot this way of thinking to it as a epistemic law, because also it is very economical. You don't need a backward process. The backward process, as the forward process, only happens in your head when you infer what is going on. So it is very economical in a way.
So, Francisco, can I ask you something related to?
Yes, of course, please,
so,
please.
Would it be right to put it in another way by saying that the second law of thermodynamics holds only for subsystems? You cannot take an isolated system and apply a second law of thermodynamics to it. I mean, everything you are saying about our knowledge of this thing, that actually inherently implies that we are talking about a subsystem because we are sort of outside it or something like that.
This is a beautiful question. This is a beautiful question. And you ask me if you're right to say that. And I would say, yes, you're perfect. Like, you know, you're perfectly free to look at it in that way. I cannot say if you're right or if you're wrong. I would say that like, I'm not sure how much we can close systems. Like, you can always assume that your theory allows you to do that in principle. But then one thing is to say that systems can be closed in principle. Another thing is to say that systems all are actually closed, like to assume that the universe is closed, ultimately, right? So in this way, yes, like this way of putting things actually tells you that you are looking upon a system, that you're learning about something that is going on. And I would say that from the, you know, ontological viewpoint is very economical. You are not, you know, assuming the existence of anything but data that reach you, and you use this data to update your knowledge. And the second law is something that has to do with the way we update our knowledge. Then what would happen if you can actually close systems? Like, yeah, you can think about it that way, but you need not do so. That's the point. Yes, probably. This is what I think. What I think, I think.
Thanks.
You're welcome. So this talk was very much philosophical in the end. But I would say that, Marco, you can be also very pragmatic about what I told you today, because at least this gives you a shortcut into the literature on fluctuation relations. Because if you take a typical paper for fluctuation relations, you see that the long part is devoted to the construction of the reverse process, where people assume the detailed balance, people assume microscopic reversibility, they take the Hamiltonian, they flip the position, they keep the positions the same, they flip the sign of the momenta, and if there is a magnetic field, you have to put a minus sign, and here and there, and you have to look at balances, blah, 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 blah. You can skip that part and go to the end, and more often than not, actually, I would say every time by now, you can just jump to the final equations just by doing Bayesian inversion. So it's a very economical, not only like ontologically economical, but also like pedagogically economical. It is much easier to explain things in this way to students rather than go through these mystical time reversal operations that is allowed by the theory, but it makes not so much sense after all physically, right? It's not something, it's not a knob. It's not that if you have a machine that does a process, it's not that you turn a knob and suddenly the machine is giving you the process reversed in time. No, there is no such a thing. To reverse a process in time is something that sometimes you cannot even do practically.
So there are a couple of more questions.
I think the universe is isolated system because nothing in going outwards from universe. We cannot falsify that. I mean, everyone is free to believe what they want because it's like speaking about angels, right? The other one, what links the quantum arrow of time to the thermodynamic arrow? What is the quantum arrow of time? I don't know exactly what you mean by the quantum arrow of time. Quantum theory doesn't have time, or at least it's very hard to accommodate time within the foundations of quantum theory. There are, there is the quantum time proposal by Wouters and Page, and lately this has been investigated a lot by our friend Lorenzo Maccone, and who also visited Patna. He's a regular guest of Patna meetings.
He also gave the talk here.
I see. About the quantum time?
No, he gave something else.
Yeah. By Lorenzo Maccone, Vittorio Giovannetti, and Seth Lloyd. But again, like if we look upon quantum theory as a mechanism that ultimately gives us classical outcomes, because I still have to meet the experimentalist that is able to witness directly a quantum phenomena with their bare eyes, right? You always have some classical filtering. You have some setups of your laboratory that are labeled by a classical index, and then you have results of your measurements that are again labeled by a classical index. And so everything there works at the level of classical inference. Right? So if we use quantum theory just as a tool to produce stochastic transition rules, then I would say that, again, there is no difference there. Like this thermodynamic arrow is there because you're learning from past. You are trying to learn the future, and you cannot do the opposite. We cannot learn the future to update the past. So
there are a few more questions.
Where? I don't see them in the chat.
Oh,
maybe before.
I can tell you. The
Yes.
quantum retrodiction, does it have any connection with the measurement?
Is it in the chat?
Yeah, it's in the chat.
Okay, quantum retrodiction.
Yeah.
Yes. Well, I would say that you can do retrodiction from a measurement outcome. So actually, this is how quantum retrodiction was initially introduced. Like Barnett and collaborators, Peg, Barnett, and a third author that I'm very sorry, but I don't remember the name right now. But in 2000, they proposed quantum retrodiction as a method to retrodict the initial conditions given a measurement outcome. So that would be a particular quantum retrodiction. You can also do retrodiction fully quantum, like imagining that your belief is described by a quantum state. So you could be in a completely like quantum Bayesian approach there, and still you would have something that reminds you of Bayes' Laplace rule. So like retrodiction is a tool that you can use in any theory. Like you have to give good reasons why you do retrodiction in some way instead of another way. There are good reasons to believe that Bayes' Laplace rule is the only rule that is completely consistent. If not, there are some arguments that tell you that if you do not reason according to Bayes' Laplace rule, you could be attacked by kind of Dutch book arguments or something like that. But you could use a different retrodiction rule. This would lead you to a different reverse process. And it would be interesting to see what kind of fluctuation results you get, right? But I would be extremely like pragmatic in these things. Just, you do retrodiction with whatever information you have. If your information is classical information, like a measurement outcome, you do retrodiction based on that. If your information is in the form of some kind of quantum state of belief represented by a quantum state, then you can do retrodiction according to that quantum piece of information. So, yeah.
One more question.
About the black hole. The
Yeah,
black hole one. Oh, this is again. Well, I already told you that I'm looking forward to start thinking about cosmological problems. Problem is that I am completely ignorant about these things. I've read something, but I have to study. to understand what is the state of the art there. So it is very interesting to see, however, that Pet's reverse map, which we understand as a form, at least, if not the form of that Bayes-Laplace rule takes in quantum theory, so the form of quantum retrodiction, appears in modern formulations of the black hole information paradox, where people do the correction stage. People have this model that black holes are mirrors, right? At some point, they will evaporate and give you back information. This information, though, will be scrambled up, but still be there. So how you can unscramble the information? You could do retrodiction, as you do when you receive output from a noisy communication channel. And lo and behold, also there, Pet's recovery map appears. And so it seems that also there is some role for quantum retrodiction argument. But, these are things that I want to learn in the future. At present, I can only tell you this kind of anecdotes, like I can only be anecdotal, nothing more than that. One more question. As you said, entropy is observer dependent. If someone from outside the universe having a complete knowledge of the universe is observing, does the entropy change for him? Also, for someone from inside the universe not having a complete knowledge is observing the universe, how will the entropy change for him? Would it be according to the second law? So here there are two observers, right? One observer is outside the universe. And okay, we can say, okay, an observer that is looking upon a closed system, okay, an isolated system. And we are saying that this observer has perfect knowledge about the state of the system. So there is no probability going on. There is no stochastic transition rule. It is just a deterministic evolution of a completely well-known state of the system. There would be no entropy change for this observer, right? You would just be looking at the evolution of an isolated system, which by definition does not change. Actually, nothing happens in an isolated system, right? You have only this kind of unitary evolution, which is just a rotation, a kind of symmetry in phase space. There is nothing really interesting going on in an isolated system, so entropy does not change. Whereas from someone inside the universe, or someone not having a complete knowledge in observing the universe, the entropy, yes, the entropy would, like, if this person is describing, so the point is that what is the second law telling us? The second law is telling us what is it that grows then in the second law, right? With this approach about prediction and retrodiction. So the thing that monotonically goes down in time is your ability to tell apart a predictor from a retrodictor. So the thing that goes down, the thing that you're losing in time, the thing that the second law is telling you is keeping decreasing or increasing anyway, is the ability to tell apart the inferences done by the predictor from the inferences done by the retrodictor. In other sense, prediction and retrodiction tend to agree more and more and more and more. And ultimately, nothing will happen. Like, you will just be looking at something that does not change, because prediction and retrodiction will actually agree. So for someone inside the universe, the second law will tell you that if you're lucky, you will be able to tell apart a predictor from a retrodictor in the same way, but typically predictor and retrodictor will tend to agree as the system evolves. Right? So I don't know if I answered the questions, but it's a very difficult question to answer. I can tell you what this interpretation tells you to think, but of course I cannot say that this is right and other interpretations are wrong. Just I find it very appealing because it's economical.
Maybe last question. There's a question. It's not question actually. This guy, Sriya Karmukar, he asked to see the slide number 19 and explain the symmetry and asymmetry.
Yes, sure. Okay. So my slides are still shared, right?
Yeah, it's shared. Yes.
Okay, so we can go back. Slide 19. Oh, yeah, the box picture. So we constructed the reverse process phi hat from the previous picture. I can go to the previous slide. We constructed phi hat from the steady state, from the invariant distribution. So by its very definition, S is also invariant for phi hat. So if you propagate S, the invariant distribution, through phi, or if you back-propagate the same invariant distribution through phi hat, you end up with S. S is invariant, both for the direct process and for the forward process. And so that's why that if the predictor and the retrodictor are given as priors, they are given the steady state, they would agree. Like if you look at a system in thermal equilibrium, if you shoot a movie of, for example, like a glass of water, right, at room temperature, and we are keeping the time it's not an equilibrium ultimately, right? But you can assume that it is, it's a good approximation to the equilibrium. So you can shoot a movie of a glass of water at room temperature. And if you show me the movie backward in time or forward in time, I will not be able to see any difference there, right? Instead, if I put the system out of this invariant distribution, right? So if I start the system with some distribution P and I let it evolve in time, or if I start my system in distribution Q and I back propagate it according to my retrodiction, or if you like the other narrative, the typical narrative that you find in statistical mechanics, if I evolve Q through the reverse process as a physical process, I will see an asymmetry. So things do not agree. And P and Q could be the same, right? As long as these are not the steady state, as long as P and Q are not the invariant distribution, you can start from Q and P being the same, but still the predictor and the retrodictor will disagree. So this means that you are able to tell time apart. You are able to tell predictor and retrodictor apart because they will disagree. And this is the origin of this asymmetry, which is an asymmetry that is there because for Bayes' Laplace rule to work, you need a prior. To construct retrodiction, to construct the retrodictive process, you need a prior distribution. If not, Bayes' Laplace rule is not able to give you anything. This only works if you have a deterministic evolution. In that case, you do not need a prior. But more often than not, whenever you have uncertain information about your system, whenever the evolution is stochastic, to construct the retrodiction, you need a prior, and that's the asymmetry.
Almost exhausted our time.
Okay.
And I would like to thank you very much for this excellent talk. And I think that many students will be inspired by this talk. It was really, truly excellent.
Professor
Panikre, you want
Thank you very much.
I am inspired, honestly speaking.
Me too.
I'll read some of these things and get back to you later. Yeah. Extremely nice talk, very enjoyable.
Thank you very much. Thank you very much.
Very, very thought-provoking.
Yeah.
Good. That's my hope. That's my hope. I don't want to say that I'm telling the truth. I just hope that more people are, keep thinking about these things. It's not, the story is not over. We still have to learn from the second law. I'm sure.
Yes. Maybe I'll send you some emails about, non-equilibrium. Because you talked about, second law. So how non-equilibrium, I'll send you some specific questions later.
Please do that. I will be looking forward to them.
Thank you.
Okay. It was a pleasure.
Yeah.
Thank you. Bye.
Bye. So Professor Puresi is in. So it's a pleasure to welcome Professor Puresi. And you can see the sessions are going on nice and easy. And Professor Puresi is from Jamia Media. Okay. And I have sort of met him in many conferences, and you can see he has two sort of intellectual obsessions. One is quantum information at the level of ground level, the particle wave duality, very simple things like, for example, double slit experiment, what it tells about how this, for example, environmental interaction collapses it in a very physical level. For example, recently I have read almost all of his papers because I have cited some of them. Extremely clear thinker. And the other thing I see him is that with a camera, taking pictures of flowers and wildlife. So you can go to his webpage, you will find out his deep interest in many things. And nature, human relationships, society, philosophy, many things. And particularly his papers are extremely readable, very readable, very clear. So with this introduction, I will ask Professor Puresi to start the session.
Thank you, Prashant, for this nice introduction. So is my presentation visible?
Yes, sir.
Okay. So today hello everybody. So I'll be talking about this very popular concept of wave particle duality, which I'm sure most of you would have heard about. And then something called quantum erasure, which has been a very long-standing controversial topic. Some of you would have heard about it. Some of you may not have heard about it. So you will get an introduction to that today. So if you have any pressing questions, you can ask in the middle also. But of course, at the end, you can have your questions set to your heart's content. So the outline of the talk is as follows. So first, I'll give you an introduction to wave particle duality using this very well-known double slit experiment. Then we'll talk about what a quantum erasure is. And then we'll go to this delayed choice quantum erasure. Okay, so consider this very simple experiment where you have a double slit and you have some particles which are coming from the source. Particles are coming one by one, and there is a screen here. Distances, of course, because of this sketch, I could not draw properly. This screen is supposed to be very far off, and these two slits are also supposed to be very close together. So suppose we close one slit, lower slit, and let only the upper slit be open. So what will happen? So every particle which comes, it will only, if it is able to pass through this upper slit, only then it will reach the screen. And of course, they're all not all in the same line because of some scatter in their propagation. There will be a distribution on the screen, and distribution will be such that you will have this kind of a pattern on the screen. There will be density of particles more at the center and tapering off on both sides. On the other hand, if you close the upper slit and open the lower one, then you see a very similar pattern. There may be a very slight or almost no shift in the pattern. And because these two slits are very close together, so the pattern will almost be similar. So again, you will see a similar pattern, and there will be more particles landing at the center and tapering off, the density of the particles tapering off on both sides. So if I ask you to guess what will happen if I keep both the slits open, our classical logic will tell you that if goes through the upper slit, it will land on this pattern because we have already tested with thousands of particles. And if it goes through the lower slit, then it should land on this pattern somewhere. This is also we have tested with thousands of particles. So with both the slits open, we should see a sum of these two patterns. But when you actually do the experiment, then you see this. This is a higher density of particles, then there is almost no particles, then a higher density of particles, very low density of particles, high density of particles, and so on. So you will see this kind of a familiar interference pattern. So you can consider this portion where you have higher density of particles as what we call the bright fringe, and this is the dark fringe. So you see an interference pattern. So you see that this is a very fascinating experiment. You can't imagine that one particle is interacting with the other particle while it is passing through the two slits, when they are passing through two slits, because I already said in the experiment, we are throwing one particle at a time. So each particle goes and hits the screen, and then the second particle comes. So how does the particle know, how does it affect the particle, whether the slit it is passing through? If it is passing through one slit, how does it matter to that particle whether the lower slit is closed or open? But here it seems to make a difference. And this kind of experiment can be done with electrons. This kind of experiment can be done with protons. It can be done with molecules. So particles which are indivisible, our classical logic tells us that particle only passes through one of the slits, and still we get this interference pattern. An interference pattern always seems to imply that something passed through both the slits, and then there is an interference. That is what we understand from interference. So this experiment, real two-slit experiment with electron, was first done in 1989, but there is a continued interest. And so this is the latest one in 2018. So you see that this is the picture of the screen. Particles which are on the screen are represented as dots. So each electron is coming one at a time. And as more and more particles accumulate, so initially there is no signature of any interference. They just look like as if they are landing at random positions. And you see that as number of particles increase, slowly a fringe pattern starts emerging. And when you have a lot of particles which have landed on the screen, you actually see that there is an interference pattern. There are more electrons in this region and very few electrons in this region. Ideally, this is supposed to be completely dark, but in reality, it is difficult to achieve that. Okay, so since it seems to defy our logic that why, if it is passing through one slit, why opening or closing of the other slit matters. So let us try to find out which slit the particle goes through if it is when one electron is passing. So suppose one electron passes and we put a tiny camera here, or any other device. I'm not specifying the device, but suppose it is a tiny camera, so that it takes a picture of every electron that passes through this. So if you get a picture, then you see that electron has passed through this slit. If you don't get a picture, that means it has passed through the lower slit. But when you put such a mechanism of detecting which path the electron is following, once you put such a mechanism in place, immediately you see that the interference pattern disappears. And what you see is what you had initially expected from your classical logic. It is a sum of these two initial patterns. This is what you get. So the moment you try to find out which of the two slits the particle went through, your interference pattern goes away. So this seems to be a very interesting phenomenon. And Niels Bohr was actually very fascinated with this. And he elevated it to the level of a separate principle. He called it the principle of complementarity. So he says that certain physical concepts are complementary. What he means is by that is that if two concepts are complementary, then an experiment that clearly illustrates one concept will obscure the other complementary one. So you can see only one concept at a time. So he says an experiment that illustrates the particle properties of light will not show any of the wave properties of light. An experiment that illustrates the wave properties of light will not show any of the particle nature of light. And you can see that in our double slit experiment with light or with electrons, what this would mean is that this which way information, this actually represents the particle nature. If you know which way the electron has gone, which slit the electron has passed through, you know that it is behaved like a particle. If you don't know that and you just see an interference, then you know that because of interference, it is behaved like a wave. So you see that, so what this principle of complementarity means that which way information and interference pattern, they are mutually exclusive. Which information or which slit information, or you can get interference, you cannot get both. So you see either wave nature or particle nature. So this is, apart from complementarity, a more popular word for this is wave-particle duality. They are both used interchangeably. So let us try to understand what is the deeper reason of complementarity using quantum mechanics. So let us see how interference arises quantum mechanically. So in a two-slit experiment, the state of the particle when it passes through a double slit, it can be written like this. This is the state corresponding to it passing through the upper slit. Let us call it slit A. And psi B is the state corresponding to the particle passing through slit B, the lower slit. State coming from slit A, state coming from slit B. See, so these two states, they travel to the screen and then they interfere with each other and then they land on the screen. And what you see there is the result. So the probability of finding the particle at a point X on the screen, you just take the mod square of this. So it will give you the probability from Bound's rule. So when you take the mod square, you see that you will get this term and you will get this term, and then you will get what these you call the cross terms. So this term multiplied with this term and so on with these complex parts. These first two terms, they represent the first two smeared out patterns which I showed you. This is the term which actually represents interference. So this is how interference takes place, that states coming from the two slits, they interfere with each other and you get an interference pattern. Now let us suppose that, let us ask what happens when you try to get a which way information. So what happens when you try to get which path information is the following. You have to make a measurement, and to go at the simplest level what a measurement would mean, you can go to this definition of measurement given by von Neumann. So he says that first essential part of every quantum measurement is that measuring device should get correlated, states of the measuring device should get correlated with the states of the system which you are measuring. So in simpler language, what this would mean is the following. So suppose this is our path detector. It is a very simple quantum mechanical system. It has only two states, 1 and 2, and these two states are orthogonal. So what von Neumann means that if there is to be a measurement, then these two states should get correlated with the two paths of the particle. So you see that you will get an entangled state which looks like this, psi A times 1, psi B times 2. So the cats represented in red are the states of the path detector or the measuring device. So let us suppose that there is an observable P. such that these states 1 and 2 are the eigenstates of this operator. So each gives a different eigenvalue. So you measure this operator, and one eigenvalue will tell you, okay, this was the state 1. The other eigenvalue will tell you that this state was 2. So now, if you see the state 1 in your measurement of the path detector or this observable P, then it implies that particle traveled through path A, because when you find this, this part will go away. That is what the collapse postulate or the measurement postulate of quantum mechanics says, that the state gets reduced. So if you get eigenvalue corresponding to state 1, then this part will go away. And then you know the state of the particle was psi A, that means it travels through path A. If eigenvalue of P is such that it corresponds to the state 2, then you can say that particle passed through path B, the lower slit. So now you see that if you want to find the probability of a particle landing at any position X on the screen, you will do the same procedure. You take a mod square of this wave function. But you see that when you take mod square here, because of these additional path detector states, you will have an inner product of these states. One inner product with 2, 2 inner product with 1. And as I said, that if you want to do a good measurement, these two states 1 and 2 have to be orthogonal to each other. If they are orthogonal to each other, but you see that these are the very terms which are responsible for interference. So the orthogonality of these two states, this will actually kill these interference term. And what you are left with, the sum of these two things, which represents no interference. So interference killed by the orthogonality of 1 and 2. So you see that here, although I have talked about using an observable P, but you see that taking this mod square, I am not even assuming that I have done a measurement on an observable P. Suppose I don't do any measurement. I just take them, I let the particle land on the screen and then count the probability of particles at every position, and still I will see the same result. So that means my doing the measurement on the path detector is completely irrelevant. It's not important. The mere possibility of getting which way information, because the which way information is already stored in these states 1 and 2 because of this entangled state. So the mere, I have a possibility of getting which way information if I want, but I may not actually get that information. So the mere possibility of that information, of this getting which way information is enough to destroy interference. It's a very surprising and interesting aspect of quantum mechanics and wave particle duality. Okay, so the first people to ask this question, that what happens if one experimentally tries to observe both wave and particle natures at the same time. So this paper was written in 1979 by Wouters and Zurek. So what their conclusion was that the more you observe the particle nature, the more it blurs your interference. If you get full knowledge of which path the particle has gone through, then interference pattern will be completely gone. But if you have partial knowledge of the which way information, then only interference will be only partially lost. It will be still there with, with some lower intensity. It will be blurred. So you can say that this is an attempt to understand wave particle duality in a quantitative manner. We are not saying either particle nature or wave nature. Rather, we are saying how much of particle nature and how much of wave nature. So let us go a bit more precise on this. So this work was done by Englert in 1996. So what he is doing is that, again, using the same kind of setup, two-pass interferometer, or rather just a two-slit experiment, and you have a pass detector. So I'm now again defining what kind of path detector is that. It could be something involving polarization or spin or any other thing. All that matters is that path detector state has only two states. Let us call them D1 and D2, similar to what our states, red states 1 and 2 were there initially. So what Englert was able to show that if you calculate visibility of interference, which is defined simply in optics as maximum intensity minus minimum intensity at any point divided by maximum intensity plus minimum intensity. So he showed that that is actually equal to the inner product of these two path detector states. And there is a measure of distinguishability of the two paths, how well you can distinguish between the two paths, whether you can tell that the particle passed through the upper slit or the lower slit, your ability to do that he quantified by this quantity D, let us call it distinguishability. And in this case, it turned out to be this 1 minus inner product of D1, D2 square and square root of the whole thing. So from here itself, you can see that if D1 and D2 are orthogonal, this visibility of interference will be 0. So that means when you have full path knowledge, then interference will not be visible. And you can see that if inner product of D1, D2 is 0, then this D will be 1. So D goes from 0 to 1, varies between 0 to 1, and visibility also varies from 0 to 1. So you can write a very nice wave-particle duality relation. This has now become a very famous duality relation. D square plus V square is less than or equal to 1. So this is a quantitative statement of Bohr's principle of complementarity, that how much of wave and particle natures can be seen at the same time. And of course, people who are interested in this issue, I can also just inform them that this concept has now been generalized to multi-slit interference also. So there have been duality relation derived for multi-slit interference also. But I'm not going to talk about that here today. Okay. So now let us move on to quantum erasure. So since I mentioned that the mere possibility of getting which path information is enough to destroy interference, the path information is stored in these states 1 and 2 path detector states, which is a quantum mechanical object. So the question one might ask is that, is it possible to retrieve interference by erasing the which way information contained in the detector? So as I said that, initially I said that observable P will tell me whether it was state 1 or state 2. I can look at another observable which will not tell me whether it is state 1 or 2, or rather it will destroy this information of state 1 and 2. If I measure any such observable, so in other words, if I erase this stored which way information, can I recover interference? So let me define these new states, which are a combination of these two states. So this state plus is 1 plus 2, and this is 1 minus 2, and these are the normalization factors. And in terms of these two states, I can write this my original state as follows. So of course, the probability of the particles landing on the screen will still not give you any interference, because you have not done anything. You have just changed the mathematics here. It will not affect the physics here. But now suppose this was proposed by Scully and Droll, and the initial idea is due to James in 1980. So suppose one measures an observable Q of the which-way detector, the path detector, such that these states which I introduced, plus and minus, these states are the eigenstates of this operator, maybe with an eigenvalue plus minus 1. So we do that before the particle hits the screen. So again, I have written the state like this. And suppose, so this is my initial entangled state. Now suppose I make a measurement of this operator Q. And remember, plus and minus are the eigenstates of this operator, and our measurement postulate tells us that you will get either this or this in a measurement. So there are two possibilities. You get the eigenvalue of Q as plus 1, or you get eigenvalue of Q as minus 1. If you get eigenvalue Q as plus 1, you know that the state of the particle gets reduced to this. This is again coming from quantum mechanics. You have to take the inner product of this full state psi with this state plus, and what you are left with this. So this will be the state of the particle once you have found out that the path detector state is plus. And you know that this kind of a sum state, this will give you interference, and this red curve corresponds to that. So you will get an interference if you just use those particles which correspond to you getting a plus 1 eigenvalue. When you get a, suppose you get a minus 1 eigenvalue, then what happens? This part is gone, and again then the state of the particle reduces to this psi A minus psi B. So it is again a sum state, but there is a minus sign. So there is a slight difference. So one can show that this will also give you an interference pattern, which will be very similar, but only very slightly shifted. It will look like this blue curve. So the positions where you have a maximum of this curve, at those positions you will have a minimum of this curve, and vice versa. So you will get two complementary interference patterns. That means a sum of those two patterns. If you sum these two patterns, then you will get this dotted line. That means you don't get any interference otherwise, which you know that once you have a path detector, you don't get any interference. But if you make coincidence measurement, the particles detected in coincidence with plus state will restore interference. And same thing happens with the particles detected in coincidence with the minus state. So this is what is called the quantum erasure. That since you have erased the information, the interference comes back. So this is a very beautiful sort of reinforcement of the concept of wave-particle duality. That in a very non-trivial way, when you have done away with the path information, your interference actually comes back. Okay, so let me summarize what we have learned till now. When you measure this observable P, so this actually detects which path the particle has gone through. If state 1 is found, state 1 of P is found, that means particle travels through path A. If state 2 of P is found, then we know that particle travels through path B, and you don't get any interference pattern. Alternatively, if you decide to measure Q, so this is our choice whether you want to measure P or whether you want to measure Q. If you want to measure Q, this corresponds to quantum erasure. If you get a plus, then you know that the particle traveled both paths A and B. Why you can say that? Because once you get a plus eigenvalue, then you know from this state itself that the state of the particle reduces to this. And this implies a sum of psi A and B. So particle follows followed both paths. Same thing holds if you get a state minus. Here again, particle traveled both paths A and B. And in both these cases, you recover interference pattern. But what is the difference between these two cases? Difference between the two cases is that in both the situations, the particle passed through both the slits, but here there is a phase difference of pi between the two paths. Here there is zero phase difference between the two paths. Here there is a phase difference of pi between the two paths. Otherwise, the particle passed through both the slits. This is what you can conclude from this. So now you understand this. Remember, this will be using in future. These states, the 1 and 2, they correspond to our path information, and these states plus and minus, they correspond to our wave property. I mean, these tell us that particle travels both the states. Now, then these same authors, they pose this question, slightly more radical one. Can the choice to erase be delayed? Can one erase path information after the particle landed on the screen? So you see that mathematical analysis doesn't put any restriction on when the path information can be erased. Because you see that in this state, suppose the particle lands at a position x. So first you take inner product with this x, you will get a similar thing, and then you take inner product with this plus, and you will end up with the same. This is actually the probability density, probability amplitude. So you will get the same probability amplitude. So basically what you need is that a coincidence counting, so coincidence measurement. So it's a joint measurement. So in that it doesn't matter whether in quantum mechanics it is well known that when you are doing a joint measurement and calculating joint measurement probability, it does not matter which measurement you do before. So our mathematics seems to say that even if you let the particle land on the screen first, and then you decide whether you want to measure the P operator or whether you want to measure the Q operator, the result will be the same. So if path information is erased after the particle is detected, it cannot obviously affect the motion of the particle through the slit. Can one choose how the particle traveled past after it has landed on the screen? Because you see that I told you already, states 1 and 2, they correspond to particle traveling one of the paths, and states plus and minus, they correspond to particle following both paths. And the particle has already landed on the screen. It would have done whatever it had to do on the way while it was passing through the two slits. And we make a measurement, we choose to make a measurement of either P or Q later. How can that affect its past? When you make a measurement, when we measure Q, it still gives you, so these experiments have been done that if you let the particle land first on the screen and then you make a measurement of this operator Q and make this coincident count with only plus states, particle only counting particles only corresponding to the plus state of the path detector, you actually do see a recovered interference pattern. And we know that the interference pattern corresponds to particle following both paths because the amplitude from the two paths have to interfere in order to give you interference. But how can you choose after the particle has landed? So this question actually confounded a lot of people, and many people initially when this proposal was given, they said that in the delayed mode, this quantum eraser experiment will not work. So does this eraser, if it works, does it have effect backward in time? Does it affect the path of the particle which it has already followed? So you might find it very surprising and maybe a bit ridiculous also, but people have actually been debating even till now that maybe there is a retrocausality, there is the effect backward in time in this quantum concept of quantum erasure. The other thing is that does delayed choice erasure actually work in practice? So we'll come to that. So these questions are still being debated. The delayed choice quantum erasure is still not well understood. So now let me tell you about the experimental realization. The first experimental realization was by the Zeilinger's group in 1995, I think, or 1991 by Mendel. Anyway, I don't remember the details. So these experiments were done with photons, then with these two experiments with atom interferometer, and all of them, they have actually demonstrated this concept of quantum erasure in practice. And this experiment by Kim, Shi, etc. in 2000, this in PRL, this was actually the first experiment which demonstrated the delayed choice, that even in the delayed mode, you can recover the interference pattern. So this quantum erasure, delayed choice quantum erasure actually works in practice also. In order to explain this quantum erasure concept, how it may work in reality, let me show you a proposal made by us using a modified Stern-Gerlach experiment. So because you all know Stern-Gerlach experiment very well, so I think it will be easier to explain it here. So you see that you have spin-off particles which are coming from here, and there's a magnet here, and there's a double slit here. So once it passes through an inhomogeneous magnetic field, you know that the particles which spin up will get pulled up, and particles which spin down will get pulled down. So particles which spin up will pass through the upper slit, particles which spin down will pass through the lower slit. So up and down, I'm talking about the Z component of the spin of the particle. So of course now the path information of these particles, this is now carried by the spin of the particle. You can find out the spin if you later see the spin of the particle is up, you know that the particle came from the upper slit. If you find the spin is down, you know that the particle came from the lower slit. So in such a case, you will not see any interference. But now suppose you put this another Stern-Gerlach magnet in the X direction now, not in the Z direction. So what it will do is it will pull the particles apart in the X direction corresponding to their X component. So X plus will get pulled in one direction and X minus will get pulled in the other direction, pulled in the other direction. And then you will see actually two complementary interference pattern emerging. When they get pulled apart, you will see one interference pattern and you will see the other interference pattern. And you will see, I have not represented it in detail because it is not a close-up of this. The bright fringe of one interference pattern is at the same location as the dark fringe of the other location. So these interference patterns are complementary. So from here, you can see how a quantum eraser can work in practice. Okay, so now let us come to delayed choice quantum erasure, because that is what has led to controversy. So again, I have represented the two-slit experiment here, that there is a source, there is a double slit, and there is a screen here. This is my X direction, and this vertical is my Y direction. And there is a path detector here, again with only two states. I have just drawn it like this. It does not matter in reality what it is a spin or it is a camera or what. It could be a very non-trivial mechanism for us. What is important is that it has only two states, states 1 and 2 corresponding to particle passing through different slits, and states plus minus corresponding to it passing through both slits. So particles emerge one at a time, pass through the double slit, interact with the path detector, land at a random position on the screen. After the particle lands on the screen, one decides whether to read out P observable or Q observable. If Q is read, particles in coincidence with plus eigenvalue show an interference pattern. Particles in coincidence with minus eigenvalue show a shifted interference pattern. If we choose to measure P, particles in coincidence with either of the two eigenvalues of P, they show an almost identical continuous pattern on the screen, which does not represent any interference. It does not represent any interference. And of course, even if you don't do any coincidence measurement, without any coincidence also, you don't see any interference. By default, there is no interference pattern on the screen. Only in coincidence with the eigenvalues of Q, you see an interference pattern. So this is the scenario of the delayed choice quantum erasure. So what is the widespread belief? Widespread belief, and here I am quoting from this paper by Englert, Scully, and Walther, who are the proponent of this point of view, and this is the most widely accepted point of view, that choice was to the experimenters. Do we want to know whether we registered an A slit atom or a B slit atom, or are we interested in the complementary property of having the plus minus states? That means complementary property, whether the particle pass through both the slits in two slightly different ways. So choice is up to the experimenter. So that is what these authors say, that this is what is happening in the delayed choice experiment. But again, then this problem of a causal effect backward in time arises, that how can you choose what the photon or what the particle did while passing through the double slit after it has already landed on the screen? Those problems are there. So can one understand the delayed choice quantum erasure better than what they have said? So for this, let us try to simplify the quantum erasure setup. So first, let us try to clearly understand on what basis we use this path, we infer the path, that this is the path the particle has followed. So this is arising simply from this entangled state. So first, let me explain to you just an entangled state, how it works. So this is what we call an EPR state. So these are two spin half particles, or in the modern lingo, we just say that there are two spin halves, 1 and 2, and their entangled state is like this. So these up and down, they denote the eigenstates of the Z component of both the spins, and this plus minus, they denote the eigenstates of the X component of the spin. In terms of the same state can be written in terms of the eigenstates of the X component also, and they look almost exactly the same. People who have dealt with EPR state, they will already know about this. This state, looking at this state, it tells you that if you measure the Z component of spin 1, you will immediately know what will be the Z component of spin 2. Because if you get this part up for 1, you know that 2 is also up. If you get down for 1, you know that the 2 is also down. If you measure the X component of spin 1, you better look at this representation of the state. This will tell you that if you get the plus state for 1, then you will get plus state for the other particle also. And if you got minus state for 1, you get the minus state for the other particle also. And these two particles may be very far apart. They are not close together. So this is how the quantum correlations work. But again, you be careful that measuring of Z component of spin cannot tell you what will be the X component of spin 2. Measuring the Z component of spin 1 cannot tell us anything about the X component of spin 2, and vice versa. Same way, measuring the X component of spin 1 cannot tell you what the Z component of the spin 2 will be. So there is no correlation between X and Z component, different components of the two spins. There is only a correlation between the same component of the two spins. This one has to be careful. And this is the concept, this basically is the concept which we are using in our path detection mechanism. And you can see that these correlations work only as long as the entangled state exists. Suppose one first measures the X component of spin 1. Does a subsequent measurement of the Z component of spin tells you what is the Z component of the spin 1 was earlier? Clearly no, because once you have already measured the X component, the entangled state is already gone. If you make a measurement of Z component on the other spin, it cannot tell you anything about the state of the spin 1 before our first measurement. So after the first measurement, the entangled state is already gone. So this second measurement will not make any sense. This is one. I'm emphasizing on this because this is part of one of the part of the confusion in understanding this delayed choice quantum erasure. You see clearly the equivalence between the delayed choice quantum erasure and the entangled spins. You can see that the states of the particle corresponding to it passing through slit 1 and slit 2, or sorry, slit A and slit B, they are equivalent to the Z component of the spin 1. And these states corresponding to it passing through both the slits, they are equivalent to the X component state, eigenstates of the X component of the spin 1. And here the states 1 and 2 of the path detector, they are like Z components of spin 2. And these plus minus states of the path detector, they are like X components of the spin 2. So now you see that if the initial state is like this, what we were studying before, our entangled state, particle passing through slit A correlated with state 1 of the path detector, particle passing correlated with the state 2 of the path detector. After the particle hits the screen, so we are now looking at the delayed mode. Suppose we don't make any measurement of this path detecting device. Let the particle hit the screen. It hits the screen in the position x0. What will be the state? State will be just take inner product of psi with x0, and you will get the following. You can see these are just complex numbers. And this state 1 and 2 are the states. So this is the state of the path detector. Now this is neither 1 nor 2. So this entangled state is gone, and it does not give you any information whether the path detector state is 1 or 2. So that information is already lost. So making another measurement, so once the particle has landed on the screen, making a path detector measurement will not give you anything. So from this logic you can understand. So you can already see the flaw in the logic of this Engler, Scully and Walther, that after the particle lands on the screen, it is our choice whether we look at the P operator or Q operator. You can see that after the particle has landed on the screen, you simply cannot get this kind of information. So to convince you of what actually happens in the delayed mode, we will simplify the double slit experiment, and a simpler version of this double slit experiment is actually this Mach-Zehnder interferometer. So if people were there yesterday, you must have seen that Anirban Pathak had already introduced this Mach-Zehnder interferometer. So it works as follows, that there is a photon coming and there is a half-silvered mirror, which is called a beam splitter. Photon partially goes here, partially goes here, from the one upper path, lower path, and this is phase shifter if you want to change the phase and so on, and these two mirrors, they reflect back, and this again partially silvered mirror which combines these two beams, and then these are two detectors. And here we have a quantum path detecting device. Again, I am not specifying what kind of device it is, but I'm just saying that it is a two-state device. I mean, it has only two states. So after the beam splitter, this is the state of the photon, psi A plus psi B. Psi A corresponds to particle traveling here, psi B corresponds to particle traveling here. And the path detector state, to start with, we have fixed as 2. If the particle interacts with this path detector, then the state flips and it becomes 1. So if the particle went through the upper path, then the state will become 1. If it went through the lower path, then it remains what it was, state 2. And what is the effect of beam splitter? What it does is that psi A state, it splits into two parts, D1 minus D2, and psi B coming from the lower part, it splits into D1 plus D2. So first you see that suppose that which path detector is not there, a simple double slit experiment or two path experiment. What it does is that without path detector, state will be this, and the effect of the beam splitter on this state will be just this. And if you use that, you will see the end result will be just D1. You will not get D2 at all. So all photons passing through this, coming from here, they all land at D1. Nothing lands at D2. So D1 registers all photons. So this corresponds to a bright fringe, and D2 corresponds to a dark fringe. So this is like a simplified double slit experiment where all the bright fringes are sort of combined into one detector state, and all the dark fringe are combined into one detector state. So this is a simplified experiment. Now with path detector, what happens? With path detector, you see that the initial state is the following. It has an entangled state. Okay, just after it has interacted with the path detector, you see that it is an entangled state. And then again, we just use the effect of this second beam splitter on the psi A and psi B by the procedure I have indicated here. And you all can do this trivial mathematics. You will get this. D1 with states 1 and 2 of the path detector, and D2 with the state 1 minus 2 of the path detector. And you see that 1 plus 2 is what? That is our plus state, and 1 minus 2 is our minus state. So end result is the following. Particles, when they land at D1, you know that because particle only lands at one of these two detectors. So when it lands at D1, you know that the state of the path detector was plus, and when it lands at 2, state of the path detector was minus. But now you remember that these states plus minus, they correspond to what? They correspond to particle traveling both paths. So in every single case, you can tell if the particle lands, photon lands at D1, you know that it passed through both the slits, and the phase difference between the two paths was 0. If it lands at D2, you know that the state of the path detector is minus. That means the particle again followed both the paths, but there is a phase difference of pi between the two paths. So you see that without anything in the delayed mode, when we let the particle hit the detectors without actually looking at this detector, path detector states, the path information is always erased in every case. So there is no way you can get which path information. So in the delayed mode, every detected path tells us whether the path detector state is plus or minus. Consequently, every detected photon corresponds to either psi A plus psi B or psi A minus B, which path information is always lost. So we don't have a choice. So we cannot, if you try to find out later, you will get a wrong answer. If you whether particle went through slit A or slit B or path A or path B, you will not get a meaningful answer. You will get nonsensical answer because you already know that this correlation tells you this fact that it has followed both the paths. Okay, so I think this makes clear what happens in the delayed choice experiment. And why it is easy to see here, because you can see that there was a confusion because there were so many output states, particle landing at many different positions on the screen. That is why it was not easy to see. And bright fringes and dark fringes are not clearly demarcated. They are overlapping with each other. But here you see that D1 and D2 are separated, and this is a very clean two-slit experiment, two-path experiment, which gives you interference, and it shows clearly that in the delayed mode, the path information is always lost. Now, can we do the same analysis for a two-slit quantum erasure? Because there you have many positions at which the particle lands. So it can be done, but the analysis is a bit more involved. Let me just show you. So you see that again, you will recognize these two interference patterns, the blue pattern and the red pattern. Blue pattern corresponds to correlating the path detector states with plus minus states of the path detector particles with the path detector. In a double slit experiment, if you correlate the path, the particles which land on the screen with the path detector state plus, you will recover this blue interference pattern. If you detect the particles which landed on the screen with the state minus of the path detector, then you will get this red kind of interference pattern. But now you see an interesting thing, that I have marked these blue dots and these red dots. At these positions of the blue dots, the probability of getting psi A minus psi B is 0. You see that at the position of this blue dot, there is a minimum of this curve corresponding to the minus state of the path detector, and minus state corresponds to psi A minus psi B. So that means if you are at this position on the, if you see a particle, see, you are basically not getting any interference by default. But when you see a particle has landed at one of these blue positions, you know that you can be sure that the state of the path detector will be plus, because the probability of the getting state minus will be this psi A minus psi B, which is 0. You can see that this is the minimum here, and in sharp interference, this minimum is actually 0. So probability is 0. Same thing happens at the red dots. The probability of getting psi A plus psi B is 0. So at least at these special points, you can be sure that the path information is fully lost, because you can say for sure whether you are getting a plus path detector state or you are getting a minus path detector state. Again, for clarity, let me say it again. At these special positions, of course, at any other position, it is very difficult to say, but at these special positions, when the particle lands here, you know immediately that the state of the path detector state is plus, not minus. if it lands at this point, you know that the state of the path detector is minus and not plus. So you know that the particle has traveled both paths. So path information is lost. So at least for these points, you can say that the particle has followed both paths. So I think my time is over, but maybe I can explain to a bit more. People will have this curiosity that what about other positions? Whether these other positions leave this possibility that you can choose to find which way information or both path information, whether you can you can erase or you can get which path information at your own disposal. So again, let me write this initial entangled state for a double slit experiment as 1 and 2. So now you see that we introduce these plus minus states as 1 plus 2 and 1 minus 2. But people who are doing quantum information, etc., they will know that these two states are not any sacred states. I can always have a phase factor. I can always have a phase factor e raised to power I theta, which does not change probability of this. And I can define these two states, which are orthogonal to each other, in this way. So let me call them theta plus and theta minus. And theta is maybe an angle. So if theta is 0, then these are our original plus minus states. But if theta is non-zero, then these are states which are a bit different. Now, if I want to write this entangled state in terms of these theta plus and theta minus states, it looks like this. So now you see that if I want to correlate my particles which are falling on the screen with this theta plus or theta minus, particles landing on the screen corresponding to theta minus, they will have a state which will be this. Not psi a plus b, but psi a times this phase factor plus psi b. What will be the effect of this? This will again give you an interference pattern, which is exactly similar, but it will be slightly shifted. So instead of this blue curve, you might have this green dotted curve. Okay, so now you see that what I'm getting at. So apart from, not this green curve, but this dot dashed red curve, this is slightly shifted. So now you can see what I'm trying to get at, that for any positions, not at the special positions, maximum of this and minimum of this, not at those special positions, at any position x, I can always find a theta such that the probability of this part will be 0. I think it will need a bit of thinking, but I think you can see that I can always, for every x, I can choose a theta such that this part will be non-zero and this part will be 0 for a particular position. So then you can be sure that the particle actually followed both paths, but with a slightly different phase difference between the two paths. Here again, you can show that the path information is lost, and there is no hope for getting path information in the delayed mode. So anyway, people who are not able to understand this, don't focus on that. If you understand the first part till the Mach-Zehnder interferometer, I think this is good enough. So the take-home message is that in the delayed mode, path information is always erased. So let me conclude. So before the particle hits the screen, one can choose to either read which path information or erase it. This can be experimentally verified. Erasing the which path information allows the possibility of recovering the interference pattern. If the particle, on the other hand, if the particle hits the screen before the path detector is read out means that you actually try to measure a P operator or a Q operator. If you don't do that, if the particle hits the screen first, which is what we call the delayed mode, then the path information is always erased. This is the message of this talk. And for further readings, people can look at these two papers. Thank you. I am ready to take questions now.
Whoever wants to ask, please unmute yourself and can ask directly.
Yeah, I would prefer that people ask directly.
Yes.
Ji, I have a question.
Yeah.
So what about the status of this original delayed choice experiment by Wheeler? I mean, what is giving any argument about the retrocausality, or it is already stopped?
No, see, Wheeler's delayed choice is very different from the delayed choice which we are talking about here.
Yeah, sure.
I mean, the inference which we make here cannot be used to say anything about Wheeler's delayed choice experiment. But again, Wheeler's delayed choice experiment, I mean, if you believe in quantum mechanics, you have to believe that particle can travel two paths for very long distances, but when the wave function collapses, the one long path may suddenly disappear. So that is the original Wheeler's delayed choice experiment. Okay, let me just say for the benefit of people who don't know what Wheeler's delayed choice experiment is, that suppose we don't have this path detector state, and photon comes and take these two different paths, and suppose these two paths are very long. So Wheeler assumed that suppose these are astronomical distances between galaxies. That light is coming from here and here. So now, if I remove this beam splitter, then photon lands at D2, and I am sure that it came from this. It came from the lower path. If it lands at D2, I know it came from this path because there is no mirror in between to mix the two paths. But now, after the photon has traveled, and you know that from the sun to earth also light takes 8 minutes. From some distant star, it may take many years to travel. After the light has reached close to us, I may decide to introduce or take away this. If I introduce this beam splitter, then I get interference. If I remove this, then I get particle nature. If I get interference, that means the light traveled both the paths, photon traveled both the paths. If I remove this, that means it traveled only one of the paths. So how can I sort of completely vanish one of the paths by my choice? So for this, I think if you believe in quantum mechanics, you have to believe that collapses do happen, and as long as the wave function is in a superposition, the reduction of the wave function or the measurement will actually destroy all the possibilities except one of the possibilities. So I think that is what will tell you what to think about Wheeler's delayed choice experiment.
Yeah. And what if your things you heard, there's a whole body of work by using that if you take the second beam splitter as just a quantum beam splitter, so in such a case, you have the chance to get the superposition of wave and particle. Do you comment on that?
Well, difficult to comment on that here, but actually, I don't think it is a big deal. And I think more mystery has been attributed to that experiment where the second beam splitter is put into a quantum superposition. It is no different from statistically introducing or removing the second beam splitter. It is actually very close to that.
Okay, you are meaning that even if you assume that your random number generator is a quantum, I mean that gives a superposition.
Yeah.
Still, in such a case, you cannot get any significant physics or significant argument you can make from this.
That is one part. Other part is that we have also shown that again, for the benefit of people who don't know about what this Alok's question is, that recently there have been some proposals and also experimental implementations of this following experiment. There is no path detector, but this second beam splitter, I told you that if you remove that, you will see particle nature. If you keep that in the path, you will see wave nature. Now what they do is that, suppose it is in a superposition of being, here and away from it. Then it is then the photon should be in a superposition of being in the wave nature or particle nature. So Alok, what we have shown is that experiment where you have this beam splitter in a superposition of being present and absent, this is exactly equivalent to an experiment where you have this beam splitter where reflectivity is not 50-50. If you have, say, 40-60, it will mimic one of those quantum beam splitter ones.
Okay.
So there doesn't seem to be any great mystery in that. Yeah.
Okay, thank you.
Yeah, I have a question.
Yeah.
Yeah, Kabir.
Yeah.
See, you mentioned about the double slit experiment.
Yeah.
See, there are these, strange paths which are allowed by like Feynman path integration. If I remember correctly, there was some work by some Japanese professor. You might know about it.
Right.
It goes again, comes back. Is it possible to see physically those kind of paths exist using the type of procedure you have used here?
No, I don't think that is possible. I don't think it gives any information regarding that, because I think, see, my personal view is that those strange paths are an artifact of using this theoretical method of path integrals. Because only within the framework of path integrals, you talk of those looping paths, which can go multiple times through the 2 slits or 3 slits. But the same analysis can be done completely quantum mechanically without going into that, treating just wave functions, where you don't talk of those 2 paths. So these kind of experiments or this kind of arguments which I'm giving, they don't throw any light on these looping paths at all.
Okay. Yeah, thank you.
There are some questions in the chat box. May I read them for you?
Yeah, sure.
So Narsimha asks, between duality relation and uncertainty relation, which one is more fundamental?
That's a good question. Actually, I think that is again one thing which should have been clarified in any discussion on wave particle duality. So there had been a long-standing controversy that the wave particle duality, what is the origin of that? So you remember this original debate between Bohr and Einstein. Einstein had proposed an experiment with recoiling slits, where he argued that you can actually get both path information and interference But Bohr then gave his counter argument showing that you actually cannot do that. And that argument Bohr used actually relied on the uncertainty principle. He showed that if you were able to do that, you would violate the uncertainty principle. Because of the uncertainty principle, you will not be able to get interference if you are getting path information. But we have shown that there is we have written a paper in 2012 in Quanta, where we have shown that this Bohr's argument can be reformulated in terms of entanglement. You may not talk at all about uncertainty principle. I can give the same argument like I have been giving, I have shown in the initial part of my talk, where the two paths get entangled with. What this would mean is, in this Einstein's recoiling slit experiment, is that this slit which the particle passes through, it recoils in different direction depending on whether the particle is going through the upper slit or lower slit. So the states of this recoiling slit will also get entangled with the two paths of the particle. And once this entanglement is in place, you can see that interference will be destroyed. So just by this existence of this entangled state, it is enough to show that interference is lost. So these are actually two completely alternate ways of looking at wave-particle duality. You can look at it from the entanglement point of view, or you can look at it from the uncertainty point of view. These are two equivalent ways of looking at that. There is no experiment where you can actually say that this can only be explained by entanglement and not by uncertainty principle, or because initially for a long time in this debate, people thought that Einstein's recoiling slit experiment can only be explained via uncertainty principle and not by entanglement. But this is not so. All wave-particle duality experiments can be explained by both the concepts. So both these concepts are on equal footing. But if you want to go to really fine detail, say multi-choice, multi-slit interference experiments, there these duality relations have relied on the entanglement. There it is not clear whether you can use uncertainty principle to formulate duality relations for multipath interference also. Maybe somebody can do it, but I don't know. But at least for two-slit interference experiments, these two things are on equal footing.
There is another question by Sayak that does the delayed choice quantum erasure experiment shows that the choice of probing the wave nature or particle nature is already known by the particle to some extent?
So now from the conclusion, you can say that which path information is always erased. So you don't have any choice. After the particle has landed on the screen, you will only get information that it has followed both paths. You cannot force it to behave like a wave. So you don't have any choice. So there's no question of your choice being known to the particle or anything like that. So particle always follows both paths in the delayed mode.
There is another question. Sudhanshu asks, is it possible to define temperature of a single electron like the particle confined in a box problem in quantum mechanics? If not, why? Please explain.
Well, that's not a question of quantum mechanics. That's, I think, more a question of statistical mechanics. I don't think it makes sense to talk about this thing, temperature of a single electron, because temperature is a statistical concept. Because loosely speaking, how would you define temperature? You would say that it is the average kinetic energy of the particles in a gas, or average kinetic energy of this. So you have to have many particles, or if you are talking about one particle, you have to have some kind of environment with which is interacting such that its velocity is changing and all. It cannot be an isolated. For an isolated electron in a quantum state, it does not make sense to talk about temperature. I hope I have answered the question. Hello?
Yeah, there are no questions in chat box now.
Excuse me, sir.
Yeah.
I was just thinking in slide number 5, where you showed the number of electrons passing through the slit, and there is an interference pattern observed for thousands number of electrons.
Yeah.
So there we send the electrons one by one.
Yes.
Okay. So if I just wanted to know, is the energy of all these electrons are the same or different?
Yeah, energy is the same.
Okay. Then in case if we have a way of finding like where is the position of the first electron striking the screen, and another way of finding what is the distance traveled by that electron through either slit. Is there a way of actually telling through which slit it is being passed, in case if you calculate the time after calculating the distance through each slit once the position of the electron is known on the screen?
No, you are using very classical logic, because if you see that if it is behaving, if it is a quantum mechanical particle, when it passes through one of the slits, this slit, there is a spread in its momentum. There is a spread in its position. So there is a scatter which is already there. So there is no way you can predict. You will prepare the electron in the same state, identical state. You can do that. Now, today there are experiments which will prepare particles you can throw one by one, which are exactly in the same state, but still they will land at different positions. So that inherent uncertainty is there always.
In case if we try to minimize that uncertainty and still try to find out if there is a way of...
Okay, so let me maybe rephrase what you may be thinking. Correct me if I'm wrong. So you are saying that suppose particles passing through this land only in this small region, and particles passing through this lands only in this small region. Then of course one can say that this electrons landing here, they came from here, and electrons landing here, they came from this slit. Is that what you mean?
No, that possibility, there's a possibility of it to spread any direction, not particularly only in that position, that I know.
Because see, if their spread is not overlapping, then they will not show any interference. For interference to happen, their spread, this pattern and this pattern, these two patterns, they should overlap strongly, then only you will see interference at the end. So there is no way of actually determining from this which slit the electron has, which slit the electron has come through.
Oh, okay, sir.
Yeah, this is even true in the Mach-Zehnder experiment. In the Mach-Zehnder experiment, if you don't have any path detector, if you just have a double slit and you block one of the paths, only one path is open, still the photon will go to either detector D1 or detector D2. And there is no way of knowing whether it came from, which slit it came from. It is very similar to that.
Okay, sir.
Is there any other question?
Okay, if there are no more questions, let's thank Professor Qureshi. Very nice talk. And I'm certainly going to read both the preprints what you have pointed out here. One is published, one is preprint.
Thank you for organizing this nice school and also inviting me here.
Thank you. And talks have been so far quite nice, and in fact, I request the students will put these papers in our academic bank so that the students should go through it and work it out. Okay. So we are going to do that.
Okay, that's good.
Thank you. Thank you.
Okay.